Hello everyone, welcome to my YouTube channel on Engineering Mathematics. In this video, we are going to learn how to find out particular integral of the linear differential equations with constant coefficients when its RHS is an algebraic expression in X. In my previous videos, we learned how to find out the particular integral when RHS of the linear differential equation is either trigonometric function or an exponential function. Links of those videos are given in the description box. Now, before proceeding to learn the technique, let us look at the prerequisite for this technique. Prerequisites is nothing but the commonly used power series for 1 plus x inverse and 1 minus x inverse. Power series for 1 plus x inverse is given as 1 minus x plus x square minus x cube and so on, whereas power series for 1 minus x inverse is given as 1 plus x square plus x cube and so on. Whenever you have a minus sign here, all the terms in this power series are positive, whereas when you have plus sign here, terms in the power series are with alternative plus and minus sign. So that's easy to remember. Now we proceed with the technique. Recall that the particular integral of linear differential equation f of dy is equal to x is given by yp is equal to 1 by f of d of x. Now we are assuming that if x is equal to x raised to m, that is an algebraic expression in x, then the corresponding particular integral, that is 1 by f of d of x raised to m, is obtained as follows. First we write this f of d as 1 plus phi of d or 1 minus phi of d by taking out the least degree element from this bracket. After writing this f of d as 1 plus phi of d or 1 minus phi of d, we take this term in the numerator. So we have 1 plus phi of d inverse of x raised to m. Now this we can expand with the help of power series that we just saw. So 1 plus phi of d inverse can be written as 1 minus phi of d plus phi of d square minus phi of d cube plus dot 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 of x raised to m. Finally, we take this x raised to m inside the bracket. So we have 1 into x raised to m minus phi of d of x raised to m plus phi of d square of x raised to m and so on. And depending on the nature of phi of d, we solve these terms. Let us understand this concept with the help of an example. Assume the given differential equation is d minus 1y is equal to x square. Then corresponding particular integral is given by 1 upon d minus 1 of x square. Since this RHS is an algebraic expression in x, we first write this f of d as 1 plus phi of d or 1 minus phi of d. To do so, I suggest that you take out the least degree term from this bracket. So here least degree term is minus 1. So when we take it out, we have 1 upon 1 minus d here with minus sign outside. Now doesn't it look like 1 minus phi of d? Yes. So let us take it in the numerator. Now we have 1 minus phi of d inverse. We can expand it with the help of power series that we have seen already. It can be written as 1 plus d square plus d cube and so on of x square. Now let us take this x square inside. So we have minus of 1 into x square is x square plus d of x square plus d square of x square plus d cube of x square and so on. Now let's evaluate these terms. Since d is nothing but d by dx, that is derivative, so here we have to calculate derivative of x square, which is 2x. Similarly, d square represents double derivative of x square, which is 2. Then of course, triple derivative of x square is 0. And the remaining derivatives of x square will also be zeros. So we neglect to write all those zeros. Therefore, corresponding particular integral of this differential equation will be now written as minus of x square plus 2x plus 2. I hope you understood this technique. Now let us see some more examples of the same technique. Here the question is to solve differential equation given by d square minus 1y is equal to 5x minus 2. Since question is to solve this differential equation, we have to find out both, that is complementary function and particular integral. So let us first find out complementary function. Corresponding auxiliary equation of this differential equation is d square minus 1 is equal to 0. Let us solve this equation. After solving, we see that roots of this equation are plus and minus 1. That means roots are real and distinct. Therefore, corresponding complementary function is given by c1 e raised to x plus c2 e raised to minus x. Now let us proceed for particular integral yp. Here it will be given by 1 by d square minus 1 of 5x minus 2. Note that RHS is an algebraic expression in x. So first of all, we'll write this f of d as 1 minus phi of d or 1 plus phi of d. Now we take out the least degree element from this f of d. Here it is minus 1. So after taking it out, we get minus 1 upon 1 minus d square of 5x minus 2. Now this term looks like 1 minus phi of d. We take it in the numerator. So we have 1 minus d square inverse of 5x minus 2. According to the power series for 1 minus x inverse, we can expand this as 1 plus d square plus d raised to 4 and so on of 5x minus 2. Now let us multiply this 5x minus 2 inside this bracket. So we have 1 into 5x minus 2, that is just 5x minus 2, plus d square of 5x minus 2, that is double derivative of 5x minus 2. First derivative of 5x minus 2 is just 5 and the second derivative will be 0. Therefore d square of 5x minus 2 is 0. So we are left with only 1 into 5x minus 2, that is just 5x minus 2 and a minus sign outside. Further, higher derivatives of 5x minus 2 are also 0, so we neglect to write them. So here corresponding particular integral is minus of 5x minus 2. Now finally, to write the complete solution of this differential equation, we add this complementary function and particular integral. So complete solution is given as c1 e raised to x plus c2 e raised to minus x minus 5x plus 2. I hope you understood every step of this solution. Let us see one more example of the similar kind. Once again, question is to solve the differential equation given by d raised to 4 plus 4d square y is equal to x square plus 1. Let us first find out complementary function. Here the corresponding auxiliary equation is d raised to 4 plus 4d square is equal to 0. Let us solve this. This is degree 4 equation, so it will have 4 roots. You can take out this d square common. So you will have d square into d square plus 4 is equal to 0. So either d square is equal to 0 or d square plus 4 is equal to 0. This leads to 4 roots as 0, 0 and plus minus 2i. These first 2 roots are real and repeated. So the corresponding CF for this is given as c1 plus c2x into e raised to 0x, that is 1. So we neglect to write it. CF for remaining 2 roots can be written as c3 cos 2x plus c4 sin 2x, as the nature of these 2 roots is conjugates of each other. Now we proceed for particular integral. Particular integral will be given by 1 upon d raised to 4 plus 4d square of x square plus 1. Since this RHS is an algebraic expression in x, first we write this f of d as 1 plus phi of d or 1 minus phi of d. To do so, we will take out the least degree element from this f of d. So let us take out 4d square from this f of d. So when I take out 4d square from here, we will have 1 at this place. So that I am writing first. And since there is no 4d square in this term, we will divide it by 4d square. So when we divide this d raised to 4 by 4d square, d square will get cancelled and we will left with only d square by 4. This x square plus 1 will remain as it is. Now let us take this 1 plus phi of the term in the numerator, keeping 1 by 4d square as it is. So now we have power series of 1 plus d square by 4 inverse. Let us expand this on my next slide. 1 plus d square by 4 inverse can be written as 1 minus d square by 4 plus d square by 4 the whole square and so on of x square plus 1. I am deliberately not writing the remaining terms of this series because we see the second derivative of this x square plus 1 is 2, so the third derivative is 0. Therefore, remaining derivatives of this x square plus 1 are also 0, so we neglect to write the remaining terms of this series having higher powers of d. Now let us take this x square plus 1 inside this bracket. So we have 1 into x square plus 1 minus d square of x square plus 1 upon 4. D square of x square plus 1 is just 2. D square means double derivative of x square plus 1. So we have 2 by 4, that is 1 by 2. So 1 into x square plus 1 minus 1 by 2. 1 minus half is just half. So we have now 1 by 4d square of x square plus half. 1 by d square is nothing but double integration of x square plus half. So let us first do single integration, keeping 1 by d outside. Integration of x square is x cube by 3 and integration of half is x by 2. Now let's do one more integration of this term. Integration of x cube is x raised to 4 by 4 and 4 3s are 12 in the denominator we will have, plus integration of x is x square by 2, so we will have 2 into 2 4 in the denominator. So finally, particular integral in this case is written as 1 by 4 x raised to 4 by 12 plus x square by 4. Now we write the complete solution by simply adding complementary function and this particular integral. So complete solution here is c1 plus c2x plus c3 cos 2x plus c4 sin 2x plus 1 by 4 x raised to 4 by 12 plus x square by 4. I hope you understood every step of this solution. Now it is your turn to solve the questions. For you, I have given 2 DIY questions with their solutions so that you can tally them. Please write me in comment box whether you are able to solve these questions or not. Also comment whether you like these videos or not. Guys, please share these videos among your friends so they will also have the benefit. Thank you all of you.
Thank you guys for watching this video. Please subscribe my YouTube channel for more such engineering mathematics videos. Please press the bell icon to have updated information about my videos.